The symbolic meaning of recycling is an episode of the Degrees of Freedom project, videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. This video is an example of a simple process flowsheet with a reactor, a separator, and recycle. The solution is purely in terms of the labeled variables for the flowsheet and demonstrates the need to go completely around a recycle loop to solve the algebraic equations. Here we have a PFD of a system with a mixer, a reactor with a single reaction, a separator, and a recycle loop. The reaction is stoichiometric coefficient of A times species A goes to the stoichiometric coefficient of B times species B, and the stoichiometric coefficient of C times species C. We'll assume the stoichiometric coefficients are known. Don't forget, negative reactants and positive for products. In addition, for this example, assume that the knowns or givens are the feed rates of A, B, and C in stream 1, the fractional conversion of A in the reactor, again, probably governed by thermodynamics or chemical kinetics, and split fractions of A, B, and C with respect to stream 4. Our goal is to solve for all of the flows, the extent of reaction, and the overall conversion in terms of the knowns or givens. In general, when calculating a problem with the recycle, you have to derive a complete set of equations around the recycle loop before you can solve for the unknowns, only in terms of the knowns. In our case, we will calculate around the loop, starting from the mixer, going to the reactor, and then to the separator before we return to the mixer. To make the derivation clearer, we will circle each known in the equations, and then circle the entire equation once we have it with a single unknown in terms of the knowns. Here's the PFD again. We will begin with the balance on species A, starting at the feed. The feed rate of A in stream 1 is a given, so that is one equation we know in full. In the mixer, the output of A in stream 5 is the sum of the inputs from stream 1 and stream 3, the recycle stream. We don't yet know the output flow, or the recycle flow, so we only know n.A1. That's one equation and two unknowns, so we can't solve it yet. In the reactor, the output of A in stream 2 is 1 minus the fractional conversion times the input from stream 5, or, substituting from the mixer equation, 1 minus Fa times the sum of n.A1 and n.A3. We know the fractional conversion, and n.A1, so we're left with one equation and two unknowns, or two equations and three unknowns. We also need to solve for the extent of the reaction, so we'll write the equation first in terms of n.A5 and the extent, then substitute in for n.A5, and finally rearrange to solve for the extent. In these equations, we know the stoichiometric coefficients and n.A1, so we're left with one equation and three unknowns. In the separator, the output of A in stream 4 is the split fraction times the input from stream 2, or, substituting from the reactor equation, which was in turn substituted into from the mixer equation, we have the split fraction times 1 minus Fa times the sum of n.A1 and n.A3. We know the split fraction, the fractional conversion, and n.A1, so we're left with one equation and two unknowns. The flow of A in the recycle stream, stream 3, is 1 minus the split fraction times the input from stream 2, or, substituting in from the reactor equation, which was in turn substituted into from the mixer equation, we have 1 minus the split fraction times 1 minus Fa times the sum of n.A1 and n.A3. We know the split fraction, the fractional conversion, and n.A1, so we're left with one equation and two unknowns. Or are we? We'll start with the last equation for the separator, n.A3 equals 1 minus Ta4 times 1 minus Fa times n.A1 plus n.A3. As before, we know the split fraction, the fractional conversion, and the input of A, n.A1. Since we've gone completely around this recycle loop, we should be pretty much done. If we look closely, we'll see that the unknowns are n.A3 and n.A3. This equation sometimes freaks students out because it says the value of n.A3 depends on the value of n.A3. This fact is why we need to go completely around the loop. If you were given this equation in an algebra class, it wouldn't freak you out at all, and you would just solve for the value of n.A3. Let's do so, and you'll see the value of n.A3 depends only on the feed rate of A in stream 1, the fractional conversion, and the split fraction. So we can now calculate n.A3 in terms of the knowns or givens. You do not want to enter any of the formulas into a spreadsheet until you have solved them around the loop, and they are all in the form of one unknown in terms of knowns. Otherwise, you'll get the dreaded circular reference error. If you get that error, go back and rederive your loop equations to eliminate it. There are occasions when you can use circular references to solve a problem. Recycled material balances is not one of those occasions. One final thought on the equations. This derivation is for the steady state flows. It doesn't describe at all the transient process to get into steady state. If you're really into differential equations and you want to set up the transient process, you can, but it is beyond the level of what we cover in these videos. Once we have n.A3, we can solve for n.A5, And then we can solve for n.A2, and then we can solve for the extent of the reaction. Continuing on, for the calculations of the B and C flows, we'll use the extent of reaction that we now know. We'll do the derivation in terms of B, and then recognize that the same set of equations, but with the B subscripts replaced by C, will work for the C flows. Starting with the overall balances, n.B4 equals n.B1 plus nu B times the extent of the reaction. n.C4 equals n.C1 plus nu C times the extent of the reaction. Each is one equation and one unknown. We now have a choice. We can start the mixer and work around the loop, or we can start the output, stream 4, and use the separator equations to solve for streams 2 and 3, and then use either the mixer equation or the reactor equation to solve for stream 5. Let's do the separator and then the mixer. For the separator, we can get the exits from the reactor from the product stream for the separator. n.B2 equals n.B4 over the split fraction TB4. n.C2 equals n.C4 over the split fraction TC4. n.B3 via n.B2 equals 1 minus the split fraction over the split fraction times n.B4. And n.C3 via n.C2 equals 1 minus the split fraction over the split fraction times n.C4. Finally, with the mixer, n.B5 equals n.B1 plus n.B3, and n.C5 equals n.C1 plus n.C3. For the reactor, since we now know the inputs, outputs, and extent of reaction, we can double check that n.B2 equals n.B5 plus the stoichiometric coefficient for B times the extent of reaction, and n.C2 equals n.C5 plus the stoichiometric coefficient for C times the extent of reaction. The summary information for the overall fractional conversion and the output flows is Fa overall is 1 minus n.A over n.A4, or Fa in the reactor over Fa in the reactor plus Ta4 minus Fa times Ta4. n.A4 equals n.A1 plus nu A times the extent of the reaction. n.B4 equals n.B1 plus nu B times the extent of the reaction. n.C4 equals n.C1 plus nu C times the extent of the reaction. The advantage of solving the full set of equations algebraically before entering the formulas into a spreadsheet is that it makes investigating parametric studies and what-if scenarios much easier. There is an example spreadsheet displayed here with the full spreadsheet available on the website that implements the set of equations we have derived. It has the set of inputs or givens that we have addressed, again with the handbook or reference values in blue and the problem-specific inputs in green. Obviously, for a spreadsheet, you have to enter the numerical values for the parameters, not just the algebraic formulas. The body of the spreadsheet is set up so that everything refers back to the input parameters, and there are no numerical constants, other than an occasional one, in the spreadsheet. The implication is that you can change any of the green or blue parameters, and everything in the spreadsheet updates. If you check the entered formulas, you'll find that they have been entered with the proper absolute and relative references to minimize formula entry and to permit easy copy and paste or cell dragging to fill in the formulas. The principles used in this example should apply to any problem with recycle. The example spreadsheet was used to generate a parametric study of the effects of the fractional conversion in the reactor and the separator product stream split fraction with respect to A on the overall fractional conversion. The data are plotted as Fa overall as a function of Ta4, with Fa in the reactor as a parameter. The overall Fa are plotted on both linear and logarithmic scales. The trends are what you would expect. As more of the reactant Fa is removed in the product stream, less is recycled, leading to lower overall fractional conversion. As the fractional conversion in the reactor increases, the overall fractional conversion also increases. The takeaways from this video are 1. It is possible to develop the general equations for a PFD with a reactor, a separator, and a recycle. 2. As the fractional conversion in the reactor goes up, the overall fractional conversion goes up. 3. As the split fraction of the reactant in the product stream goes down, the overall fractional conversion goes up. Thanks for watching. This video was brought to you by the DOFPro team.